All right, well, welcome to another lovely end of the week here in calculus. Today, what we're going to do is keep playing with derivatives and specifically the chain rule. We developed the chain rule a couple days ago. Last time we used it to find derivatives of inverses. Right? We saw that inverses have derivatives that are reciprocals of each other. And today we're going to play around with chain rule some more and actually be able to attack things that are not functions. I'm going to show you how you can actually differentiate things that are not functions, which can be kind of handy, right? But anyway, so that's our goal for today. But before I do that, I'm just curious if there are any questions on homeworks, anything we want to go and look at. All right, so Eric just gave me a couple here. He wants to look at numbers 7 and 8 from section 3.4. All right, I'll go ahead and put those on the list here. Any other ones people want to see? Okay, well, we'll go take a look at those, and then if anything else comes up, if you guys think anything else you want to see, we will go and take a peek at them. All right, so let me go ahead and share my screen again. Okay, so I'm actually showing you, we're getting here a different way. If you look at my screen, you go, holy cow, that doesn't look like Canvas. You're right. It is not Canvas. This is my open math, which is what makes your homework assignments. I just happen to have this one up and ready. So we'll go ahead and find that here. But same questions, just looks a little bit different in terms of this portion. Okay, so here are 7 and 8. So for 7, and again, yours may have slightly different numbers, but so it says, suppose P of T represents the population of a certain mosquito colony, where T is measured in days. The current population of the colony is known to be 596 mosquitoes. Okay, so then it says, if P prime of 0 is 69 mosquitoes per day, estimate the size of the population in 11 days. All right, so we all kind of cool with what they're asking us to try to do. Like they're telling us how many mosquitoes are here right now, and we want to make a guess of what it's going to look like, how many there will be in 11 days. So let's look at the information that they gave us. Obviously, the 596, when they write here, the P of 0 equals 596, that's saying at time 0, right now, there are 596 mosquitoes. But then it says if P prime of 0 equals 69, right? So 69 mosquitoes per day. What does that mean? What does P prime of 0 mean?
The derivative.
Okay, so it's the derivative
At
of
0.
P at time 0. So that's like right now, that's the derivative. And in the context of this problem, what does this number mean? Like, yeah, it's the derivative, but what is the derivative?
The population. The derivative of the population at 0 days.
Okay, but what does that mean though? What does the derivative of a population mean?
Is it the growth rate?
Yeah, it's the rate of change. Remember that derivatives are rates of change. So this is the change in the population right now. And even look at the words. It says mosquitoes per day. So right now we know that we should expect in the next day an increase in the population of 69 mosquitoes. Okay, so that's basically the slope of the tangent line right now, 69 mosquitoes every day. So we're told how many we have right now, and we're told how it's changing right now. And we're going to use that to make a guess of how many they're going to be in 11 days. Okay, so let me go to a whiteboard real quick. Let's clear all that stuff. Okay, so basically here's what's going on. We've got a graph. I'm just going to draw a graph, and I have no idea if this is what it really looks like, but we're going to go with it. No, hold on. Let me erase those two. All right. Sorry about that. Okay, so let's say that here are axes. Okay, so this is a graph of our population versus time. So here's T and here's P. Now, again, don't look at this black thing and be like, oh, that's the graph of the population. I don't know that. I'm just throwing something out there. Okay, but here's what we do know. We do know that this point right there, we know its value. We know its Y value. That was that initial population, right? So in this case, that was the 596. Right? We also know the rate of change, which means we know the slope of the tangent line. So if I look at this tangent line, I know that this thing has a slope of 69. All right, now let's think about what we're trying to do. They asked us to estimate. And you guys really have to love something that just says estimate, because when we estimate, we're just making a guess. But somewhere out here, 11 days later, we want to get an estimate of this Y, right? This is really what our goal is. We want to know, what is this? Now, in order to know that, we'd have to know the black function, right? But we don't know the black function. So instead, we're going to use the green function, because the green function, we actually can get an equation for it. It's a tangent line. There's a point on it. We've got a slope. We can use that to figure out what its value is at 11, right? We can figure that thing out, and we're going to use this as our estimate. So this is one of the uses of derivatives, right? Is we can use this to approximate the function. You remember the example I did with it's like the square root of 4.1 or something like that. And we used the tangent line to make our guess. And so we found out that our guess was like 2.25. The calculator actually says the square root of 4.1 is like 2.23. But we saw that it was a pretty decent guess, right? So Eris, when you say that could be so different, you're right. I mean, there could be a huge difference depending upon how much the function actually deviates from the derivative. So you're right. Can you give me a better way to make an estimate though? I mean, yeah, and that wasn't meant to necessarily be a, I mean, that's reality, right? Like, if all I know is that right now there are 596 mosquitoes and we're changing at a rate of 69 per day, the best I can say like literally the very best I can say is that in 11 days, it's going to be, well, it was that 596 plus 69 times 11, right? That's the best I can tell you. Am I going to be close? I don't know. I have no idea, right? I have no idea exactly how this function is growing. Like if it was this black one, that estimate is, I mean, I don't know, probably not great. But what if the function was actually, say, that, right? And now we're going, oh, okay, well, that estimate's not too far off. But it also could be that maybe our function does something like that. Whoa, that's not a function. What if it does something like this? And we're going, okay, well, that's the actual value. And now our guess is way off, right? And so you're absolutely right, there is that it's like, it could be incredibly different, but it also could be very close. And so it really just depends on how the function is actually deviating from that line. It could be exact. It could actually be 100% right. The function could be growing linearly and then we, have got it. But this is the best that we can do. And obviously the shorter that this horizontal, this X, or in this case, T gap is, the better our approximation is going to be. And that's absolutely true. So in general, if you're going to do this in real life, if you're going to use the derivative in real life to approximate what's going on, you want to make sure that it's over a very short period. Because the bigger that step, the more potential error there could be. Anyway, so, and believe it or not, this is just line. This is good old mx plus b, right? The y-intercept was 596. The slope was 69, and our step, well, we're going 11 over. So we're just using the equation of the line, but that's kind of the approach here. Anyway, so does that kind of make sense? This definitely brings up something else, and I think I mentioned this with you guys, is that we in math classes as math students, we do not like estimate. We do not like best guess. We do not like approximate. We don't like those words, right? We don't like those at all. But sometimes they're very appropriate, and sometimes it's all we can do. And I will just tell you that in later calculus, you're going to see how to approach a problem like this where what you know is the derivative only. If you know some things about the function, you can actually find out what the function is. Like we could find exactly what this black function is, knowing this initial information, if we just know a little bit more about how the function is changing. And in the real world, right? Some of you know that I did spend some time as a scientist for a while. I was doing oceanography. I was looking at how tides move sediment, and we knew rates of change. Like that's something you can always find. You can always go out, like let's talk about a mosquito population. You could go out and literally count mosquitoes and see how that population is changing. So you know rates of change easily. Finding the function itself, that's where the challenge comes in. But in science, that's primarily what is done. So it's using this information to make a good estimate or create even a model that fits it really, really well using some other tricks. Anyway, so that's this one. And let me go back to the other question, because I think the other question was similar, right? Let's look at that because you also asked about number 8 eras. And so number 8 here says current population of a small town is 4,921 people. It is believed the town's population is tripling every 9 years. Approximate the population of the town 5 years from now. Okay, so this one, it's not quite the same, but it's kind of similar, right? We're told how many people we're starting with, 4,921. And we're also told how it's changing. We're not told how many people per year, but we are being told, oh, it's tripling every 9 years. So let's kind of see what we can do to get an estimate for this one. So let me write down this information and then we'll go to the whiteboard again. So 4,921. Triple in 9 years. How many in 5? All right, so let's go back to the whiteboard and let's see what we can do about this one. All right, so let me just clear this picture and we'll start anew. Okay, so again, here's what we've got. We've got the population at 0 is 4,921. So are we going to use the linear equation again? Absolutely. We want to make a guess for P of 5. But what we know is that it triples in 9 years. Okay, so that we actually know P of 9. P of 9 is going to be 3 times this. Right? They told us it triples every year. So in 9 years, we should have 14,763. Okay, well, here's what we know, right? We've got at time 0, we got 4,921. At time 9, we've got 14,763. And so we want to know, what are we going to get at 5? Well, if this is all the information we have, what we can do is another linear equation, right? We can actually just connect the dots on these. Use that line and then run up here at t equals 5. All right, so we've got 2 points. Those 2 points are enough to get the equation of a line, right? We just need to get the slope. So the slope's going to be 14,763 minus 4,921 over 9 minus 0. And then the y-intercept is 4,921. Let me go ahead and actually just get this number for you. That's going to be 9843, or sorry, 42 over 9. Yeah, errors, these are a lot simpler than you think, because when you use the derivative, you're just using lines. So let's see, this gives us a 109. No, we'll just leave it like that. So we get that y is equal to 9842 x plus 4921. That's our y-intercept. And now we just take 5 and we fire it in there. All right, so again, that's best we can do right now. We'd absolutely love to be able to get a better estimate for this, but right now, that's all I know. And the problem is, if all I know is that this population triples in 3 years, I don't know how these 2 points are connected, right? I mean, it could be that kind of function. It could be this kind of function. It could be, not likely, but it could be this kind of function, right? And the problem is I have no clue which of these dots am I actually looking for, right? Um, so the best I can do right now is just say, well, it's going to be on average kind of here. All right, so is that better for this one? Yeah, all right, good. Okay, so any other homework questions before we hop to the whiteboard and start doing other stuff? All righty, well then let me just go ahead and stop my sharing here and get back to my screen, and we'll go ahead and switch views. So I will be right back. All right, so last time we played around a little bit with inverse functions, and we saw how inverse functions derivatives were related. We saw that they were reciprocals. We just had to really pay attention to that swap of y and x, right? But what allowed us to do that was the chain rule, right? We started with that f of f inverse of x equals x. We differentiated both sides, we used the chain rule, and it got us our formula, right? Well, today we're going to use the chain rule to help us with things that are not functions. So let me just start with an example of what I want to do. Suppose I ask you this question. All right, I'm going to give you an equation here. X squared minus y squared equals 1. All right, so this is the graph. There's a graph of this, right? There's something.
A circle?
Graph. All right. Ooh, so is it a circle? Was that you, Susanna?
Yes.
Circle. What do you guys think? Is that a circle? That's actually a really good guess, but it's not a circle. If it was,
is it because it's missing a plus sign? It's because it's supposed to be a plus, not a minus.
If it was a plus, pardon me here for a second. If it was a plus, it would be a circle, but it's not. It's a minus. So it turns out that it's actually a hyperbola, right? Yeah, obviously. Okay, well, anyway, so it's a hyperbola. And actually, if you want to draw the graph of it, let me just kind of remind you what hyperbolas look like. This one is going to have a graph that looks something like this. Don't fret too much if you don't remember exactly how to get to this real fast. That's okay. That's not really integral to this discussion. Sorry. It's a little calculus humor. That's not really that important. But what I want you to notice is that this is not a function, right? It fails the vertical line test. And so everything that we've done with differentiation so far requires a function. Okay, so we don't have a function, which means, what are we going to do? But what if I wanted slopes of tangent lines? What if I said, okay, out at this point right here, I want to know the slope of that tangent line? Because maybe I want to approximate this graph with a linear function. Or maybe not that point. What about this point? Maybe I want to know the slope of that tangent line, or the tangent line here or here, right? Like I can actually attempt to do the same kind of thing that we've done before, except it's not a function. And the definition of the derivative, the way that we approached it was the derivative of a function. Okay, so we got to do something different, right? We have to somehow either make this a function or figure out some other kind of trick so that we can actually do this. Well, you can actually attack this both ways. So think about functions. With equations of functions, you can always write those as y equals, right? You can always write them as y equals. So one option we have, I'm going to put this here as an option. So option number one, we can solve it for y. So if you have an equation like this, you can always start by solving it for y. Once you have it solved for y, you can differentiate like normal. Okay, so that's our first option. And you can see for this one, that's actually not that bad if we want to solve this for y. If we move some stuff around, we're going to get x squared minus 1 equals y squared. And at this point, we take a square root. But I am going to remind you that when you take a square root, we got to do a plus or minus. This is what makes it so that it's not a function, right? You have options. You have options for your y depending on your x. You plug in an x, you can either have a positive or negative, or it doesn't work with functions. So we are able to solve it for y, but here's kind of the issue. Again, there are options, plus or minus, and which one we use is going to depend on which of these points we're trying to find the derivative for. Basically, the way that this breaks down is if we were just look at the positive is the upper half of this. So I'm going to go ahead and color this part green. So if you were just to look at the positive is this green, these green pieces, and the negative would be the red. So this kind of sucks because we're going to have to know which side we're on to know which one of these things we want to differentiate, right? And if I give you a whole string of points and said, okay, find the derivative, find the slope at all these different places, you're going to have to bounce back and forth between the plus one and the minus one and keep track of where you are, and that can get a little confusing. But at least it's doable, right? Like if I gave you a specific point, like let's say that we're out here at this point, which is going to be 2 negative root 3. And I said, let's find the slope of the tangent line here. We actually have enough information to do that now. We would start by using the negative square root. So our function here for the bottom half would be f of x equals negative square root of x squared minus 1. What we're really looking for then is f prime of 2, right? We're trying to find what is the derivative when x is equal to 2. What's the slope of the tangent line when x is 2? All right, well, let's do that because this will help us remind us of the chain rule because we've got a function inside another one, right? So if we've got f of x, let me rewrite it. Instead of that square root, we saw that it's much easier to use exponents. So let's make that a 1/2 power. So let's do the chain rule. So remember how that works. First, we've got a minus here. That's a -1 times. So that's a constant multiple. It's just going to stick around. But now for the chain rule, we differentiate the outer function first. So that's u to the 1/2. So we're going to get 1/2 times x squared minus 1 to the minus 1/2. And then we have to multiply by the derivative of the interior function. And what's the derivative of x squared minus 1? All right, beauty. Thanks, Aries. It's 2x. All right, so we're going to multiply that by 2x. So let me just rewrite this because the 2's cancel. I'm going to get a minus x over the square root of x squared minus 1. And so now I could plug in my 2. And this is going to give me that the slope of this line, let's say, is 2 over the square root of 3. So easy enough. We answered the question, right? It was just a matter of doing some algebra to get us as a y equals, and then differentiate like we always do. All right, well, so now you might get to the question of why is Bruce even talking about this, right? If we've already got a way, if it's just a matter of solving for y and doing it, why not just do it, right? Isn't that how mathematicians are? We got a way, let's do it. Well, mathematicians are also lazy, remember, right? Like we love being able to do something. It's our kind of our hard-headed nature, right? Tell us we can't do something, we figure it out. But we're also kind of lazy. And if there's a faster way, we're going to take it. And really the issue here is the start. It's the solving it for y. Algebra is a pain. You guys have seen that. Algebra is always a pain. If we can get away from the algebra, we want to do it. And you can imagine that this equation can be so gnarly that trying to solve for y might not even be possible. So we have to kind of keep that in mind and go, well, maybe there's a better way of actually doing this. And there is. And that's what I'm going to show you. It's called implicit differentiation. So we're going to attack this problem in a slightly different way. That's going to make it so that we don't actually have to do all the algebra. All right. So let's talk a little bit about implicit differentiation. So we'll come back to this example in a second. So this is going to be option number 2, by the way. All right, so implicit differentiation. So let's think about what this means, and let's just kind of break it down using English language. So implicit, same root as imply or implied. So what does that mean if I imply something or something's implied?
You don't explicitly say it, but we have to assume it.
Okay, so I love how you just used explicit with implicit because those are like opposites of each other, but yeah. So explicitly stated means it's like it's out there, right? If I'm going to explicitly tell you something, I'm just going to be real upfront and just tell you exactly what's going on. Implicit or implied, if something's implied, it means that it's not told to you directly, but it's hinted at. Right? So here would be me implying something to you. And obviously, this doesn't apply in reality. That's why I'm even doing this example. You're like, man, I think you need to take a shower. Okay, so if I say that, what am I really meaning? What are some things that I'm implying that I'm not specifically stating? If I just go, oof.
That you smell bad.
Yeah, I just said, you smell. Right? I didn't use those words. If I just came out and I just said, oh man, you smell really bad, that's explicit. If I beat around the bush, if I go, oof, you need a shower, or what is that, you know, or anything like that. I'm hinting at what I'm trying to say, right? That's what it means to imply something. Okay, so implicit differentiation means something's not being told to us directly. And what that thing is what our function is. All right, so with implicit differentiation, what's going on is that we're going with the fact that it's implied that y is a function. Okay, we just don't know what it is. If we were specifically told y is the function x squared minus 1, that's not implied anymore, that's explicit. So all the differentiation we've done so far is actually explicit differentiation. It's differentiation where we're told specifically, here is the function. But implicit differentiation, we're going to go with, okay, we're going to say y is a function. You just don't know exactly what that function is. Okay, so that's all this means, is that we're going to treat y like a function. It's just going to be an unknown function. All right, so then the question is, how does the whole differentiation thing actually work here? Well, if y is a function, when we differentiate it, we're going to need the chain rule. Okay, so here's how this breaks down. With implicit differentiation, all of the x terms they're treated like normal. Okay, we're going to do to the x's what we always do. But all of the y terms, they're going to require chain rule. Because y is a function. We just don't know what it is. So like if we have y squared, our function is being squared. That's composition. It's a function being put into another chain rule. If we have sine of y, that's a function being put into another function. We're going to need chain rule. Okay, so all the terms that have y's, they're going to require chain rule. But other than that, we can treat it exactly the same way. All right, now I know when I put this into words, it doesn't really mean anything. So let's go back to that example. Let's go back to that example of the hyperbola. Let's take that equation and let's differentiate it implicitly. All right. So go back to that equation. Remember that equation was x squared minus y squared equals 1. So what I'm going to do with that equation is what I've done with every other equation. I'm just going to differentiate both sides with respect to x. So you remember when we did this, hopefully with the inverse example, where we took both sides of the equation and differentiated. We're going to do the same thing here. All right, so let's start with the right, because the right-hand side is easy. What's the derivative of 1?
Zero.
It's just 0. Constants, they just disappear. So this side of the equation is going to equal 0. All right, so let's go to x squared. What's the derivative of x squared?
Just x. I mean 2x.
It's going to be 2x, right? We bring that 2 out front as a multiple, so we're going to get 2x. So we just differentiate that like normal. Now, with the y, this now is chain rule. So think about how the chain rule works. It says we differentiate the outer function first. So if I were to differentiate y squared, I'm going to get 2y. But then the chain rule says multiply by the derivative of what's inside. Well, that means I need the derivative of y. But I know you're going, but Bruce, we don't know what y is. Well, class, you're right. You don't know what y is. So what we're going to write is the derivative of y. I'm just going to write y prime. So that's how we're going to attack the chain rule when we use implicit differentiation. What's y? I don't know. What's its derivative? Y prime. Right? I mean, if someone were to ask you, what's the derivative of y? You go, the derivative of y. It's kind of a silly answer, right? That's the kind that gets you slapped. But that's what we got. We don't know why. So the best I can tell you is the derivative of y is the derivative of y. All right, well, okay, there's the derivative, taking a derivative of both sides of this equation. But notice what we can do now is I've got a y prime. I can actually solve this for y prime. So let's do a little bit of algebra. I'm going to move all that y prime stuff onto the other side. So I get 2x is equal to 2y times y prime. To solve for y prime, I just need to divide both sides by 2y. So the 2's cancel. And what we now have, let me go ahead and box this, because as always, the box tells us we're done. But what I've got is a formula for y prime for the slope of the tangent line at any point. And you notice that I don't care if I'm on the top half of this hyperbola, the bottom half of this hyperbola, I don't care where I am. But what I can tell you is that the derivative slope is going to equal x divided by y, no matter where we happen to be. So if you go back and you look at the example that we did with that hyperbola, remember we were at that point 2 negative root 3. So think about that. If I plug that into my derivative here, I'm going to get x over y. And so I get minus 2 over root 3. And if you go back, look at your notes, or later if you're watching this on YouTube, if you rewind a little bit, you're going to see that that's the slope that we found when we solved the equation for y, differentiated, plugged in the x, and so on. All right, so it got us to exactly the same point. I would argue that this is way faster and way easier. I don't know if you agree, right? And it's fine if you don't agree. But just look at what we did objectively. We still did some algebra, right? Don't think that there was no algebra in this example or in this method, but the amount of algebra we had to do was way less, right? I literally moved one thing to the other side and then divided. Right? People that are first learning algebra can do that. The other one, I had to move things over, take square roots. Square roots had to have plus or minuses. Right? So the algebra was easier in this. But even better, think about the calculus. The calculus, all I did was power rule. I just had to remember the chain rule multiplied by y prime. Compare that to the calculus that we had to do the other way. That was like legit chain rule with square roots and all that. That got gnarly fast. So implicit differentiation can actually save you a lot of time, even if it's something that's not terrible to solve for y. Okay. So looking at this, I just want you to notice again with the x's, you treat all the x's like normal. You do with them what you always do with them. The y was actually treated like you would normally. We just had to remember to multiply by y prime because the chain rule requires the derivative of what's inside. All right, so you can do this with any kind of equation. I can give you x's and y's, any kind of equation. We can always use implicit differentiation to find a formula for the derivative. Now, it's usually going to involve both x and y, which is okay. And in fact, a lot of times we will know specific points and we're good to go. So let's do another example. Let's go to a circle. So circles are pretty easy. Again, they look a lot like the one I just gave you, but let's look at this guy. X squared plus y squared equals 25. And we're going to find the slope of the tangent line. And I'm going to give you at a specific point. Let's go with -3 minus 4. So there's a point on the circle. You can see if you plug those in, -3 squared is 9, -4 squared is 16, 9 plus 16 is 25. So let's see if we can find the slope of the tangent line there. I don't want to bother solving this for y and going through the derivatives. Instead, let's use the chain, or let's use implicit differentiation. So we're going to start like we always do here with implicit differentiation, which is to take a derivative of both sides with respect to x. All right, so x squared gives us a 2x. The y squared, we're going to get 2y, but the chain rule says multiply by y prime. On the other side, derivative of 25 is 0. So again, I'm going to solve this for y prime. So we'll move the 2x over by subtraction. Then we'll divide by 2y. And so what we get now is that the derivative is negative x over y. Very similar to what we saw with the other one. It's off by a sign, but that probably doesn't surprise you too much because the equation of a circle is very similar to that of the hyperbola. All right, well, now if we want to find the slope of the tangent line at that point, just plug those numbers in. So we're going to get m is equal to -3 over -4, which gives us a -3/4. Watch all the minus sign. All right, well, there you go. We just found the slope of the tangent line to the circle at that point. Fast. Fast, fast, fast. All right, so before we go to more complicated examples, how are we feeling about the concept of implicit differentiation? Silence is deafening.
It makes sense.
All right, thanks, Susanna. You guys know about the reaction buttons, right? Thumbs up. Thumbs up. Okay, I'm seeing some thumbs up, so I'm gonna trust that this is going okay. And the more of them you see, the easier this becomes. It's just a matter of every time you deal with y's, attach on a y prime because you're doing chain. All right, well, so this is definitely an example where you might go, yeah, but we still don't need to use implicit differentiation. We can do it the other way. And, some people are definitely old schools, right? This is the way that it's always been done. This is how it works. Let's do it. Right? I know I've got a bit of that in me. But let me show you how, there are times you can't solve for y. And then in that situation, you gotta do it. All right, so here's another one. Let's try this guy. And I'm not gonna make this too terrible, I hope. But let's just go with this guy. Let's say we've got x squared plus sine of y plus y cubed equals, let's go 4 minus xy. All right, so x squared plus sine of y plus y cubed equals 4 minus xy. Now, there is a graph. This thing definitely has a graph. What it looks like, I have no clue. We could just find x's and y's, start plugging them in and get some points and start connecting the dots, and maybe we start seeing what that graph looks like. That's kind of irrelevant right now. Okay. But what I do know is that there is a point that's on this graph, and I want to find, this time we'll do the equation. Let's find the equation of the line tangent at the point 2, 0. So 2, 0 is a point on this graph. If you plug in x equals 2, y equals 0, you do see that you get truth in this equation. So there's definitely a point on that graph. And let's find the equation of the tangent line there. All right, so our go-to of solve for y and differentiate is gone, right? Imagine trying to solve this for y. You get y all by itself. There are 3 terms with y, first of all. One of them's in a trig function. Yeah, no, this ain't gonna happen, right? We're not gonna be able to solve that thing for y. But we're not sunk, because we can do implicit differentiation. So let's differentiate both sides of this with respect to x, and let's see what that does for us. All right, so here we go. Let's ddx. So we'll just take them in order. So x squared, its derivative, 2x. Because remember, x's we treat like normal. All right, what's the derivative of sine? All right, cool. Cosine, thanks for remembering. So the derivative of sine is going to be cosine. So we're going to get cosine of y. Right? Sine of y is derivative is cosine of y. But since y is a function, remember it's implied, that's a function. Since y is a function, we need to multiply by y prime. Okay, so now let's go to y cubed. So the derivative of y cubed is going to be 3y squared. But again, since y is a function, we're going to multiply by y prime. So there's a derivative of the left-hand side of this equation. It's 2x plus cosine of y times y prime plus 3y squared times y prime. All right, so we good there on the left? All right, cool. Thanks for the thumbs up. Okay, so now let's go to the right. Let's just keep going. All right, so we have a 4. Well, it's constant. Constant's going to go away. And then we have minus x times y. All right, so now this is where we got to be a little bit careful because now we need the product rule. We haven't seen product rule in a while, so this is good for us to practice it. But why do we need product rule? Because it may not actually seem like we should. Why is it that we need product rule?
Because we have x times y and we have to treat them differently.
Okay, so the key word is, think about what you just said earlier. You said we have x times y, right? As soon as we've got multiplication, we have to use product rule, and y is a function of x. It's implied that it's a function of x, so we have to treat it as such. So we are definitely going to have to use the product rule here. So let's set up the product rule. Here are the two things that we're multiplying. We've got x and y. So we need their derivatives. The derivative of x is 1. The derivative of y is y prime. And remember, with the product rule, we just do the whole multiply one times the other. So when we put this together, we're going to get, for our derivative, first of all, there's a minus sign here because of the subtraction. But then we're going to get y plus xy prime. Right? It was 1 times y plus x times y prime. Okay, so let me just warn you. With these homeworks and things. This is going to be where you make mistakes. You're going to forget. You're going to see like x, y, and you're not going to actually remember and go, oh, wait, that's two functions being multiplied together. That's x being multiplied to this other function, y. All right, just this is where the mistakes are going to happen, because it always happens when people are learning implicit. So watch out for that. Pay very close attention to when you get x times y. All right, well, here you go. We just took a derivative of both sides, and yeah, we're pretty much there, right? Okay, now, since we're just doing this at a point, at 0.20, we can go ahead and plug that point in right now. We can just literally put in x for 2, 2 for x and 0 for y. So let me show you what we're going to get when we do that. So we're going to get 2 times 2 plus the cosine of 0 times y prime plus 3 times 0 squared times y prime. So that's that side. If we look at what that is, this gives us a 4. Cosine of 0 is 1. We get 1 times y prime. And then the rest of it is 0. On the other side, if y is 0, okay, that's gone. X is 2, we get minus 2y prime. Our goal is to solve this for y prime. So if we move things around, we get 3y prime equals 4, or y prime equals 4/3. So there's the slope of the tangent line at that point. I know nothing about the graph. Can't even picture it. I know nothing about the function y. Doesn't matter. I now have a derivative, so the tangent line at that point. And now we can do anything that we've ever done with derivatives. If I want to approximate where this graph is going to be, if I take a little step, I can use this line. If this equation is describing the motion of a particle, this tells me the velocity. Right? This is the speed at that point. All of those different uses that we've ever used the derivative for, we can now use on this random weird equation. All right, so we answered the question, found the equation of the tangent line, but I want to do one more thing with this. There's a reason I didn't write down below, because I want to do some algebra. Because another really handy thing to do is to actually solve this for y prime. So sometimes we're going to want to do this algebra. If we want to solve this for y prime, we need to move all of the pieces that have a y prime in them together to one side, and everything without the y primes, move them to the other side. So let me just move a couple of things. I'm going to move the 2x over to the other side. And I'm also going to bring this xy prime to the side that has all of the y primes. So basically, I just moved this guy over and this one over.
Bruce, would you be able to read what that top left line says quickly? I just can't tell what that says.
Way up here?
Yeah.
Okay, so it's 2 times 2 plus cosine of 0 times y prime plus 3 times 0 squared times y prime.
Thank you.
You're welcome. Yeah, that was just putting in the 2 and the 0 in to the equation. All right, so now that we've got all these guys with y primes, we're going to factor the y prime out. So we can get y prime times cosine of y plus 3y squared plus x. So when you have more than one y prime, which will happen a lot, you're going to go ahead and bring them all together and then factor it out. And then you can divide by that factor. And so the reason that we do this is now we've got a formula for the slope of the tangent line at any point, at absolutely any point on that graph. So I could go ahead and plug the x equals 2 and the y equals 0 into here, and we would get that as well. So I just turned the light in my room. I'm hoping that that helps balance the sunlight that's really bright here. I think it just made everything else really dark. Hopefully that helps a little bit with that, being able to read. Real quick aside, I don't know if you guys have noticed this, but you can actually tell that the seasons are changing on us just by watching these videos. Have you noticed that the light has been moving, the sunlight? Like when we very first started, I never got blinded by the sun. Now we start class and the sun is like right in my face. And that's because, well, it appears to us that the sun is moving position, but it's because the earth is moving position because we're going through the seasons. So it's going to be really interesting to see that come December, like the very last day of class, I'm curious to see what the light's going to look like. We also are going to get affected by daylight savings time when we shift that hour, but I don't know. It's how my brain works. It's really kind of freaky. Pay attention to everything and notice everything. But anyway, I digress. All right, so hopefully you guys are seeing that the process is no big deal. It's just differentiate like normal. Just every time there's a y, you attach on a y prime. All right. But this example really shows you that even if we're in one of these situations where we can't solve for y, we can still find the derivative. We can still find the slope. All right, so questions on that one? All right, give me 1 second. I'm going to adjust my blinds. We're going to see if we can go without sunlight, if that helps the board a bit. I'm not liking how much glare we're getting. Oh yeah, that's definitely better. I just have to avoid a new spot. Okay.
Can I ask one quick question?
Yeah, absolutely. Go for it.
Just to clarify, the original question that you asked was finding the equation of the tangent line, right? So that was just plugging it into point slope form, and then what you were showing us was just like an additional way to solve for the slope anywhere?
Correct. Yeah, and actually, thanks for reminding me. We didn't actually finish the question that I asked, right? Shoot, I forgot I asked for the equation of the tangent line. We just have the slope. But now that we've got the slope and we've got a point, let's get that real fast. But yes, Alia, the only reason I showed all of this is that sometimes you want just the equation for y prime. You're not told at any specific point. And so you need to go through this algebra. So that was just an aside for this one.
Great, just making sure I understood the question there.
Yep, no, absolutely. And I'm glad you asked. So, and that actually just reminded me that I didn't finish answering what I wanted us to do. So there's the equation of the line tangent to that graph at the point 20. All right, so good question. Any other questions on this one? All right, so how are we feeling about implicit differentiation?
Probably
All
should
right,
practice over the weekend.
Yeah, I'm going to take your silence as well. Okay, there are a couple ways I could take your silence. One, I could take it as you're completely overwhelmed and you're just like completely clueless and have no idea. I'm not going to take it that way. I could also take it as nobody's paying attention and I'm just talking to myself. I'm not going to take it that way either. I could also take it as, yeah, everything's kind of making sense. We're feeling pretty good. And that's how I'm going to take it. So I'm going to choose to take it that way because it makes me feel better. And in the absence of other stuff. But I think, Susanna, you're right that this is one of those things that when you practice it, once you do it, you'll see that it's not really that bad. I mean, it's a matter of just going through the process. But basically, it's the same differentiation rules, all the same rules. Just every time there's a y, we have to make sure that we attach on a y prime. We have to multiply by the derivative because that's the chain rule. We just don't necessarily know what that function is, right? Because it's implied that it's a function. So we just make sure that we attach on a y prime. All right. Okay, well, I know that we're a little bit early in terms of wrapping up for the day, but I don't want to start a new topic just yet. And I don't really feel like doing another example of this unless you guys really want. I think you guys, it seems to me that you guys are feeling a little bit, burnt out. So I think we're going to stop here, but let me give you a plan for what's coming up. Okay, so first, homeworks. Remember that the next set of homeworks are due Monday night at midnight. I'm going to double check because we're like right on the verge of being on schedule, off schedule. I want to make sure that I'm not having you guys do homeworks that we're not ready for. So I'm going to make sure that the last homework that's due for this class is going to be the implicit differentiation section. All right, so if there's anything beyond that, I'm going to extend it. So I'll check that out after class. But don't forget to get in there and work on homeworks. We will have a chance on Monday to talk about them. Again, just to clear up any other questions. And what we're going to do next time is we're going to actually figure out the derivatives of exponential functions and logarithmic functions. So we're going to get a couple more under our belt. You may have been wondering if we were ever going to get to those. Yeah, we'll get to them. But those are the big classes of functions that we haven't dealt with yet. So we'll develop their derivatives. And then after we get those built, we're going to just keep applying this stuff. All right. So that's our plan for the coming days. And if there are any other questions, I'll go ahead and be happy to answer them.
Is the quiz that we were going to have today moved to another day?
No, I'm just going to work instead of having, I think I originally said we were going to have 6 quizzes. Now we're going to have 5. We're just going to have 1 less. But that was a good question. All right, any other questions? All right, well, hey, with that, have a wonderful weekend, and I will see everybody on Monday.